All right, everyone get ready, because today we're taking a deep dive with you into the world of quantum neural networks.
Oh, yeah.
We're going to be checking out this essay by Yogo Schneeppat
Okay.
that really digs into some wild possibilities for where AI could be going in the future.
It is wild. It's definitely exciting territory.
Yeah.
We're talking if you could take all the power of AI that we know
Right.
and boost it with quantum mechanics.
Oh, wow.
That's what we're talking about.
So these quantum neural networks.
Yeah.
Or QNNs.
The QNNs.
Like the cool kids call them.
The cool kids. Yeah.
That's not just like a sci-fi fantasy. This is
no.
This could be reality.
What Schneeppat's highlighting is that QNNs could really change things in fields like medicine.
Okay.
Like they could lead to totally new drugs.
Right.
By simulating molecules at the atomic level.
Oh, wow.
It's not just speeding things up. It's like opening up possibilities we haven't even thought of.
I am so intrigued.
Yeah.
But I'll be honest, the whole quantum realm still feels kind of like magic to me.
Sure.
So can we just do a super quick quantum 101?
Yeah.
Just so I don't get lost when we start talking about the QNN part.
Of course. So the main thing to remember is that quantum computers, they work with qubits.
Okay.
Which are kind of like the bits in our regular computers.
Right.
But they're way cooler and way more powerful.
Okay.
A bit can only be a 0 or a 1.
Yeah.
But a qubit can be both at the same time.
Whoa, hold on.
Yeah.
Both at the same time.
Both at the same time.
That's breaking my brain a little bit.
It is pretty wild. It's because of this thing called superposition.
Superposition.
Yeah, think of it like a coin spinning in the air. It's not heads, it's not tails.
Right.
It's this weird in-between state
Okay.
until it lands.
Right.
That's the power of superposition.
I'm picturing the spinning coin.
Yeah.
Okay.
Okay.
So where do these quantum neural networks actually come into play?
Right.
How do they actually work?
So just like regular neural networks, QNNs are made up of these interconnected nodes.
Okay.
But instead of being like regular nodes, these are made up of qubits.
Okay.
And instead of simple wires connecting them, they're linked by something called quantum gates.
So these quantum gates are kind of like the logic gates we have in a normal computer.
Exactly.
But for qubits.
Exactly. And these gates, they can manipulate the qubits in all sorts of crazy ways.
Right.
They use superposition and entanglement to do computations across multiple possibilities at the same time.
Whoa.
It's like exploring every path in a maze simultaneously.
That sounds incredibly powerful.
Yeah.
But also incredibly complex.
Yes.
I'm guessing there's some serious challenges to actually
Oh, yeah.
building and using these QNNs.
Huge challenges. Yeah. One of the biggest is that qubits are super finicky.
Okay.
They're really sensitive to any kind of interference.
Oh, really?
Even tiny temperature changes or vibrations can throw them off.
Wow.
It's a big problem called decoherent.
Decoherent?
Yeah, and it makes it really hard to build stable quantum computers.
So is it kind of like trying to build a house of cards
Yeah,
in the middle of a hurricane?
pretty much. And then there's the problem of scaling.
Right.
To really get the most out of QNNs,
Yeah.
we need to be able to control and entangle thousands or even millions of these qubits.
Yeah, that sounds like a pretty big task.
It's a huge task.
So massive potential, but also
Yeah.
some serious technical hurdles.
Absolutely.
What does Schneeppat say about the current state of research in this area?
Well, he emphasizes that it's still early days,
Right.
but there's a lot of excitement.
Oh.
Things are moving really fast.
Okay.
Researchers are exploring different ways to build QNNs,
Okay.
and we're starting to see some really promising results even with these small-scale systems.
Okay, so it's a race,
It is.
and things are moving quickly.
Absolutely.
Okay, we talked about the basic building blocks.
Yeah.
But how do these QNNs actually learn?
Okay.
How do we teach them
Right.
to solve problems?
That's a great question, and it's one of the big differences between quantum and classical neural networks.
Right.
The way we train a QNN is by carefully tuning the parameters of those quantum gates
Right.
to get the outcome we want.
So it's like finding the right settings on the quantum gates
Exactly.
to make the QNN do a specific task.
Yeah, and because we're dealing with quantum mechanics, this training process is usually much more complex
Right.
than with traditional neural networks.
Right.
We have to use special quantum algorithms to optimize those gate parameters
Right.
to make sure the QNN is actually learning.
Okay, that makes sense. But can we ground this in an example?
Sure.
Like something a bit more concrete?
Yeah, let's use Schneeppat's example of drug discovery.
Okay.
Imagine you're trying to design a new drug to target a specific protein involved in a disease.
And I'm picturing a scientist
Yeah.
in a lab with
Yeah.
all the beakers and test tubes and everything.
Right. But instead of doing all those experiments in the lab,
Right.
which takes forever and costs a lot of money, imagine simulating the interactions between the drug and the protein,
Oh, wow.
like at the atomic level,
Right.
all inside a quantum computer.
So the QNN is like a virtual laboratory?
Yeah.
So we can test tons of drug candidates without having to actually make them.
That's the idea. And because QNNs can use the power of quantum mechanics, they could simulate these interactions with a level of accuracy and detail that's just impossible for classical computers.
So we could discover new drugs and treatments much faster.
Yeah.
And maybe even find cures for diseases we've been struggling with for years.
Exactly. And that's just one example.
Wow.
Schneppot talks about how QNNs could change fields like materials, science,
Right.
finance, and even AI itself.
Okay, this is getting really exciting.
It is.
But before we get too carried away,
Yeah.
you mentioned qubits are super sensitive.
Right.
What if there's an error during a calculation?
Oh, that's a great point.
Could that have some pretty serious consequences?
It could, because even a small error in a qubit state can mess up the whole network and give you totally wrong results.
So reliability is a big concern.
It's a huge concern. Researchers are working hard on ways to reduce these errors.
Okay.
And there's been a lot of progress,
Right.
but it's definitely something that needs to be addressed before we can fully trust QNNs with important tasks.
Okay, so powerful potential.
Yeah,
Significant challenges.
Yes.
A lot of research still to be done.
absolutely.
Where do we go from here?
Okay.
What are the next big questions that scientists are trying to answer about QNNs?
That's a great question. That's a great segue, because there's a whole other level to this we need to talk about.
Okay.
We talked about how QNNs work in principle,
Right.
but there are some amazing developments happening right now that could make them even more powerful.
Okay.
One area that's really hot right now is something called quantum generative adversarial networks.
Quantum generative adversarial network.
Yeah, or
Wait.
QGANs for short.
QGANs?
Yeah.
Is that like the JANs
Yeah.
we hear about with AI art?
You got it. QGANs are basically the quantum version of those same networks.
Okay, that's officially blowing my mind.
Yeah.
Can we take a quick pause here?
Sounds good to me. We'll pick this back up in a bit.
Okay, we're back and ready to tackle these QGANs.
Okay.
I'm still trying to wrap my head around quantum neural networks, and now we're adding generative AI to the mix.
Yeah, it's definitely a hold on tight moment in the AI world, but
Yeah.
the basic idea behind QGANs, it's actually pretty similar to their classical counterparts.
Right.
Remember how we talked about those classical GANs using two networks
Yeah.
that kind of compete against each other?
Yeah, it's like one's trying to make a fake masterpiece and the other's like the art critic
Right.
trying to spot the forgery.
That's a great analogy.
Yeah.
And in the quantum world, we're basically doing the same thing,
Okay.
but with quantum neural networks as our players.
So we've got a generator QNN that's trying to create data
Yeah.
and a discriminator QNN that's trying to figure out if it's real or fake. And they're playing this quantum game of cat and mouse,
Yeah,
constantly learning and improving.
exactly. And what's really cool is that by using quantum stuff like superposition and entanglement,
Yeah.
QGANs could create and analyze data in ways that are impossible for classical GANs.
Okay, I am officially in science fiction land now.
Yeah.
But can we bring this back down to earth a little bit?
Okay.
What are some like real world applications
Okay.
of these QGANs?
Well, you mentioned AI art before.
Yeah.
Are we going to have like quantum powered deepfakes?
Yes, that's
That's one possibility. But I think the bigger impact might be in areas like scientific research.
Oh, okay.
Like, imagine being able to create synthetic data for really complex systems
Okay.
that are hard or even impossible to study directly.
Like what kind of systems?
Let's say materials science.
Okay.
Like, let's
Yeah.
say you're trying to make a new material
Right.
with special properties.
Right.
Maybe something that's super strong, but also really light.
So a new alloy for building spaceships or something.
Yeah, exactly. But experimenting with different materials in the real world can be expensive and time consuming.
Right.
What if you could use a QGAN to generate a whole bunch of data
Cool.
on hypothetical materials
Oh, wow.
with all their simulated properties?
So instead of mixing chemicals in a lab, we're using a quantum computer to
Yeah.
explore all these possible materials.
That's it. And the QGIM could help us go through all that data and find the best candidates for real-world testing.
Wow.
It could really speed up the discovery of new and amazing materials.
That's amazing. It feels like we're just scratching the surface of what's possible with QNNs and QGNs.
Yeah.
But you said earlier that quantum computers are still kind of in their early stages.
They are, yeah.
So how do we bridge that gap
Right.
between this incredible potential and where we are now with quantum computing.
That's where the idea of hybrid quantum classical computing comes in.
Hybrid,
yeah.
So combining both quantum and classical approaches.
Schneppat's essay points out that it's unlikely we'll be able to solve every problem with just a quantum computer anytime soon.
Okay.
They're still really expensive and complex to build.
Right.
And they're prone to those errors we talked about.
Yeah.
So it's about using each technology for what it's best at.
Okay, so playing to their strengths.
Exactly. With a hybrid approach, we can use classical computers for things they're good at,
Right.
like data pre-processing,
Right.
running familiar algorithms,
Okay.
managing the overall workflow.
Okay.
And then we can use the QNN for the really tough parts.
Okay.
The parts that are perfect for quantum computation.
So it's like a tag team.
Yes.
Each computer doing what it does best.
Exactly. Can I give you a concrete example?
Yep, please.
Okay, let's go back to that drug discovery scenario.
Right.
Imagine you have a huge database of potential drug molecules.
Okay.
Millions or even billions of candidates.
Way too many to test in a lab.
Way too many. So we can use classical computers to do a first screening. Maybe using traditional machine learning to look for promising characteristics.
Okay.
This could narrow it down to a smaller set.
Okay.
Like a few thousand candidates.
So the classical computer is kind of pre-filtering the data.
Exactly. It's like a first-round audition for these molecules.
I like that. Yeah.
And then those top contenders, they move on to the QNN, running on a quantum computer.
Right.
The QNN can simulate those molecules in much greater detail,
Right.
analyzing their interactions with the target protein at the atomic level.
So it's like the classical computer is the talent scout.
Yeah.
And the QNN is the judge at the final audition.
That's a great way to think about it. And by combining the strengths of both approaches, we can tackle these super complex problems that neither computer could solve on its own.
This is all really exciting, but I keep thinking about the ethical implications.
Yeah.
If QNNs can do all these amazing things, what's to stop them from being used for bad stuff?
Right.
Like, could this technology fall into the wrong hands?
That's a really important thing to consider. But remember, this episode is focused on Yurgo Schneppat and his essay, which is all about the technical side of QNNs and their potential applications.
Right.
It doesn't really get into those ethical questions.
Right.
Maybe that could be a deep dive for another episode.
Yeah, that's a good point.
Yeah.
Let's stay focused on the science for today.
Okay.
We've covered a lot.
We have.
QNN basics.
Yeah.
QGAN's hybrid computing.
Right.
What's the key takeaway you want our listeners to walk away with?
I think the big message here is that QNNs are a real technology that's developing fast, and they have the potential to change so many parts of our world.
Yeah.
From medicine and material science to finance and AI.
Right.
QNNs could help us solve some of humanity's biggest challenges.
It's a really powerful message.
Yeah.
A lot to think about.
Definitely.
Well, on that note, it seems like we've reached the end of our deep dive.
Not quite.
Oh, well.
There's one more piece we need to look at. Those new quantum algorithms that are specifically made for training these networks.
Okay, so we've built our amazing QNN.
Yes.
We figured out how to combine it with classical computing.
Right.
But now we need to actually teach it what to do.
Exactly. That's where these new algorithms come in.
Okay.
They're the key to unlocking the full potential of QNNs.
Right, so we'll pick up there next time. All right, we're back and ready to tackle that last piece of the puzzle.
Okay.
Training these powerful but really complex QNNs.
Yeah.
You were about to tell us about these new algorithms that are made just for this.
Yes, exactly. So think of it this way.
Okay.
We've built this amazing machine.
Right.
A quantum neural network that can do things no regular computer can.
Right.
But now we have to give it instructions. Teach it to learn and solve problems.
Right.
That's where these quantum algorithms come in.
Okay, so they're like the training manual for our QNN.
Exactly.
But we talked about how training a QNN involves adjusting those quantum gates to get the result we want. How do these algorithms actually help with that?
Imagine you're trying to find the perfect settings on a machine with like tons of knobs and dials.
Right.
You could just twist them randomly.
Yeah.
But that would take forever.
Right.
These quantum algorithms are designed to search through all those settings and find the best ones for the quantum gates way faster.
So they're like a really smart search engine.
Yeah.
For the perfect QNN settings?
That's a good way to put it.
Okay.
One of the most promising algorithms is called the Variational Quantum Eigensolver, or VQE.
VQE. Okay, adding that to my quantum vocabulary.
Yeah.
What makes this VQE algorithm so special?
What's cool about VQE is that it uses both quantum and classical computing.
Okay.
In a really smart way.
Okay.
It uses the quantum computer for the main quantum calculations.
Right.
But it uses a classical computer to guide the whole process.
So it's another example of that hybrid approach.
Exactly. And that makes VQE perfect for where we are now with quantum computing, where we have these small and kind of noisy quantum computers that can really benefit from a little classical help.
Okay, so VQE is helping us train QNNs.
Right.
But we also talked about QGANs.
Yes.
Those quantum generative adversarial networks.
Yeah.
Do we need different algorithms to train those?
Yes, we do.
Okay.
We're starting to see new algorithms designed specifically for training QDNs.
Okay.
Remember, QGNs have two competing QNNs.
Yeah, the generator and discriminator.
Exactly.
Right.
So the training has to optimize both of them at the same time.
Right.
It's a pretty tough challenge.
It's like trying to train two dogs at once.
Yeah.
Each with their own trick.
Exactly. But researchers are figuring it out.
Okay.
Developing algorithms that can handle this back and forth between the generator and discriminator.
This is all incredibly complex.
It is.
But I think I'm starting to get the big picture.
Good.
We've got these powerful QNNs.
Right.
We're figuring out how to use them with classical computers. And we're developing these really advanced algorithms to train them.
Yeah.
It feels like we're on the edge of something huge.
I think Schnepphat would agree with you there.
Yeah.
As you pointed out in his essay, QNNs could totally change things.
Yeah.
From medicine and materials science to finance and artificial intelligence.
Right.
We're still early on.
Right.
But the progress is so exciting.
Well, I think that wraps up our deep dive into quantum neural networks.
Yeah, it does.
Thanks for coming along with us on this wild ride.
Thanks for having me.
It's been fascinating to learn about the potential of QNNs.
Yeah.
And I can't wait to see what the future holds.
It's gonna be amazing.
Thanks again to Jorgo Schnepphat for his insightful work in this area.
Absolutely.
And to all of you listening out there, thanks for joining us on this deep dive into the incredible world of quantum neural networks.